Since any quantity, such as length, can be measured in several different units, it's important to know how to convert from one unit to another. For example, 1 meter is equivalent in distance to 3.281 feet. We can use this fact whenever we need to convert from meters to feet. For example, the highest waterfall in the world is Angel Falls in Venezuela. The water over this falls drops a total distance of 979.0 meters. What is this drop in feet? When converting between different units, we write them down explicitly in the calculation and treat them like algebraic quantities. We take advantage of the fact that multiplying or dividing by 1 does not alter an equation. For our simple example, we know that 3.281 feet equals 1 meter, or 3.281 feet divided by 1 meter equals 1. We multiply our equation, length equals 979.0 meters, by this factor of 1. Since we treat the units like algebraic quantities, the meters in the numerator and denominator will cancel, leaving us with units of feet, which is what we want. Notice I could have also multiplied our length equation by 1 meter divided by 3.281 feet, but then the units of meters would not cancel. Knowing that we need to end up with feet helps us use the conversion in the proper orientation. Using a calculator, we find a value of 3,212.099 feet. However, the rules for significant digits dictate that the answer must be rounded to only 4 significant figures, since that is the accuracy to which we know the original quantity of 979.0 meters. Thus, we round our final answer to 3,212 feet. If you need to review the rules for significant figures, see Appendix B in your textbook or ebook. One last note. The conversion factor, such as 3.281 feet equals 1 meter, has no effect on the number of significant figures, since it is defined precisely. Let's now look at an example where several conversions are required. Let's convert a typical highway speed in your car, say 65 miles per hour, to meters per second. Here, we're going to have to do 2 conversions, one from miles to meters for the distance, and one from hours to seconds for time. We take advantage of 2 well-known relationships, namely 5,280 feet equals 1 mile and 3,600 seconds equals 1 hour. As a result, our 2 conversion factors of 1 will be 5,280 feet divided by 1 mile equals 1, and 3,600 seconds divided by 1 hour equals 1. Multiplying by both of these factors gives us the following. Notice how the units cancel to give us the result in feet per second. Now we just have to use our previous conversion of feet into meters to get the final result with the units of meters per second. Notice we round our final answer to only 2 significant figures to match the precision of the original quantity, the 65 miles per hour. In addition to their role in guiding the use of conversion factors, units serve a useful purpose in solving problems. They provide an internal consistency check that helps eliminate errors. Only quantities with the same units can be added or subtracted. Thus, if you find yourself adding 12 kilometers to 25 miles, you should stop and reconsider. Either the 12 kilometers needs to be converted to miles, or the 25 miles needs to be converted to kilometers, so that the 2 quantities have the same units. In the last part of this section, we want to discuss what's called dimensional analysis. We have seen that many quantities are denoted by specifying both a number and a unit. For example, a distance of 8 meters, or a speed of 25 meters per second. Whether in meters or miles, distance is measured in length, and the unit of time could be measured in seconds or hours. In physics, the term dimension refers to the physical nature of a quantity and the type of unit used to specify it. Some of these include length, which is symbolized by an L in square brackets, time, and mass. Many physical quantities can be expressed as combinations of these fundamental dimensions. For example, speed will have the dimensions of length over time. We can use dimensional analysis to check mathematical relations for the consistency of their dimensions. For example, let's consider a car that accelerates from rest to a speed v during a time t, and we wish to calculate the distance x the car travels, but we're not sure if the correct relation is x equals 1/2 vt squared or x equals 1/2 v times t. We can determine the correct expression by verifying that the dimensions on each side of the equal sign are equivalent. If the dimensions are not the same, then the expression is not correct. For the first expression, we have length equals speed, or length per time times time squared. Since dimensions cancel just like algebraic quantities, and pure numerical values like 1/2 have no effect on dimensions, we have length equals length times time, which cannot be correct. For the second expression, we have length equals length per time times time, or length equals length, which is the correct expression. Dimensional analysis can be a powerful tool to identify if an expression could be possibly true, at least in terms of its dimensions.